All right, a continuation of section 4.4 is modeling like a real world trigonomic problem. And so because when we think of trigonometry, we are always rotating in a continuous circle. So anything that kind of repeats itself in the real world is going to create a trigonomic equation. Okay, so for example, the depth of water, d of t in meters, in a seaport can be approximated using the following formula. So if you think about the tides of the ocean, the tide of the ocean comes in and it comes out, right, at a regular pattern over time, right? So because it's continuing this regular pattern, it's going to create this trigonomic function. So the trigonomic function given is 2.5 sine.
Karen Sidarthan to the booth room, please. Karen Sidarthan to the booth room.
So the equation is 2.5 sine 0.164 pi of t minus 1.5 plus 13.4. So for today, we're just going to learn how to take this equation, graph it on our calculator, and answer these questions from it. In our next chapter, trigonomic functions, we're going to get deeper into what all of these values mean. Okay, but for today, we're just going to simply write this equation, right, in our calculators. So 2.5 sine of 0.164 pi, and then that still needs to be multiplied by x minus 1.5. And then I'm going to close a second bracket. So as you notice on your calculator, you're going to open one bracket, and this is technically on your, in the equation, all in a set of brackets. Okay, and then I'm going to add a 13.4 after that. So when you think of seaport, and this is talking about tide of the ocean, where d is in meters and time is in hours after midnight, you kind of want to set up your tables to relate to that information. So x is going to represent our time. There's no such thing as negative time, so I'm going to start this as a -2, just so I can still see my zero hour mark, which is midnight. And then technically I'd almost want to see what's happening to the ocean, at least within a 24-hour period, if not more. So I'm going to put this to approximately 30 hours. Okay, my scale of 1 is fine. And then here is my depth of the water. So again, the depth of the water isn't going to go below 0, okay, but the maximum height of the water, if I think about the sea, this is kind of just a guess sometimes, but I'm going to guess around 20 meters. Okay, and then if you hit, the other thing before I hit graph is any word problem that relates to, because we're talking about distance versus time in the question, right? This is where radians is so important, because radian is an actual number in relationship to pi, but pi is 3.14. This is where our calculator will always be in radian mode, because if we put it in degree mode, right, there's no such thing as, you can't really compare time in as a degree value, but time can be represented as a radian value, because radian is just a number, whereas degrees is like a degree, like a specific number that relates to an angle. So this is why the radian measure is so important to work around. So now that this is radians, I'm going to hit graph, and what we get is this regular movement of what's happening in the sea, right? So initially at midnight, whatever this value is, right, the depth of the water is going up, it's coming down, it's going back up, it's coming back down, so it's following this continuous pattern. So how deep is the water at 6 a.m.? Well, this function represents our depth of the water after midnight. So 6 a.m. would represent 6 hours after midnight. So if I go second trace to number 1 for value, I'm going to type in my hours after midnight here, which are 6. And so the depth of the water at this point would be 15.2 meters. Okay. We'll just round everything to 1 decimal place. What time is the depth of the water at least 12 meters high? So what I'm going to do is I'm going to, as a second y equation, I'm going to type in my depth of 12 meters. I'm going to hit graph. Okay, and the first point where it's, and we'll just find the first point. So this point here, I'm going to press second trace, and I'm going to go to number 5 for intersect. I'm going to move my, because there's more than one intersection point, I'm going to move my cursor over to close to this intersection point, hit enter a second time, and then enter one more time, and I get a intersection point of 8.75. Just double checking my equation here. Yep. Okay. So what does that mean? 8.75. It means that this point, right? What time is the depth of the water at least 12 meters high? Okay. This is going to be at 8.75 in hours or in minutes would be 8:45 a.m. Okay. And then it says, what time of day is the tide in and tide out? Write a general expression for all the times the tide is out. Okay, so when is the tide out? So if we go back to this graph, right, we don't necessarily need this point anymore. Okay, so the high point is when the tide is going to be in, and our low points are going to be when the tide is out. So what I want to do is I want to find this minimum point. So I'm going to go second trace, number 3 for minimum. I'm going to move my cursor over, hit enter, left bound, right bound, and I get this value of 10.65, let's say. Okay, so this is the first time that it's out. So in terms of a time, if I take that 0.65 multiplied by 60, this is approximately at 10:39 a.m. Okay. All right, so this is tide out. So now looking back at my graph, I need to figure out, right, how long it takes for the graph to reach back to its tide out point. So in this case, I'm going to find this other x minimum. Go over here. And then the difference between these two values will give me how long it takes for the tide to come in and out. Oh, I messed that up. Sorry. Enter. Okay, so my other point in time is 22.84. Okay, so the difference between these two values, if I should take the difference between them, try that again, is 12.19. Okay, so in general, write a general expression for all the times the tide is out. Okay, so my general expression, well, the first time it's out is at 10:39 a.m. And then I'm going to add 12 hours and 0.19 is approximately 11 minutes. So I'm going to add 12 hours and 11 minutes to this. How many times am I going to do this, right? Technically, the tide comes in and out forever, right? So then I would have to multiply that by n, where n belongs to, in this case, I'm not going to belong it to integers because I'm not going to subtract time from this. I'm always adding time. So in this case, n would have to belong to my whole numbers. Okay. The other question, it did ask what time of day is the tide in. So if we quickly found that point as well, the tide in point on my graph would be this first, we'll just find this first time is this high point. So we're talking a maximum here, number 4. Move my cursor over. And I get a value of 4.55. So again, I want to convert that to time. So 0.55 in minutes would be 33 minutes. So this would be at 4:33 a.m. Okay, so kind of lots going on in this question. General expression. All right, and lastly, example number 2, it says the alarm in a noisy factory is a siren whose volume, V decibels, fluctuates so that T seconds after starting, the volume is given by the following formula. So again, if you can think of a siren going off, even like a police siren, right? The sound has this frequency that goes high and then it goes low and then it goes high and then low. So it's repeating this regular pattern, which can be referred to as a trigonometric function. So in my calculator, I'm going to type this equation, 18 sine of pi over 15 x, close that bracket, plus 60. So again, we're talking now seconds, and we're talking about like a siren going off. Like if you think about a siren and how long it takes for that pattern to continue. So now our x value is in seconds. 30 seconds, I would say, is way too long for it to hear like a full repeat of the siren. I would say this should go down to like maybe 4 seconds, right? Like you hear this go, or maybe put it back to 10, okay? And then our y value is representing how loud that sound is, right, in decibels. So fairly loud sound is a fairly high decibel. So I'm going to put this to like maybe 100 decibels. Okay, and so here is our graph. So it looks to me I kind of overshot the time that it takes. So the alarm actually takes a lot longer for it to repeat its pattern. So I have it at repeating every 10 seconds. I might want to change this to a minute. So let's change that to 60 seconds. So this looks a little bit better, right? So sometimes you have to adjust those window settings to get kind of the graph that you're looking for. And it says, what are the maximum and minimum volumes of the sirens? So obviously we're going to find these maximum minimum points. And we're looking for the, we'll do minimum first, since our cursor is over here. Enter, right bound, enter, enter. So the minimum, right, this is the time it takes to hit the minimum, but our decibels is 42 decibels. And then we're going to now find the maximum. And you could have went to either maximum, it wouldn't have mattered. This would be 78 decibels. So that volume is fluctuating between 42 and 78 decibels. And then how loud is the siren after 2 seconds? Well, this is our time. So if you go to second trace, number 1 for value, and simply type in your 2 seconds, the answer is 67.3 decibels. Okay, and those are some examples of real-world trig problems.